In this video, I'm finally going to start talking about light polarization, which will, in the next video, bring us into electron spin. And so first, I thought I'd just talk a little bit about what light polarization actually is. And so you may or may not have heard that that electromagnetic radiation is a wave like this, and you can see that the electric field oscillates in one direction and the magnetic field oscillates in the perpendicular direction, and both of them oscillate in perpendicularly to the direction in which the wave is propagating. And you can see on this figure here, it shows we have this single wave in the electric field here, and this single wave in the magnetic field here. But you can imagine that this could be offset by some small number of degrees in sort of around this whole z-axis here, as long as they remain perpendicular to the z-axis. And so when you have light where it is in every direction, where the electric field, which is the one we're going to be kind of concerned with, but just always remember that there is that magnetic field perpendicular to that. But if we just think about the electric field here, we can see that it can be oriented in all directions. And if we have non-polarized light, then we do have it oriented in every direction. And that's kind of what this is showing right here, where you can see that these waves are offset. And you can imagine there are amplitudes in every direction in between as well, and going all the way around this z-axis, the direction of propagation here. And then we can have that run into this thing, which is a polarizer, and that will essentially block all of the light that is oriented in any direction besides a single one. Then we get this what is called linearly polarized light. It's also possible to get circularly polarized light, but I'm not going to talk about that just yet. And so you see here that when it hits some detector, that it is polarized only in this up and down direction here. And so the next thing that you can think of, you have your unpolarized light, you send it through a polarizer so that it's polarized only up and down, and then you send it through, and then you have that same light go through a second polarizer. That polarized light's now going through a second polarizer, and what happens is you get polarized light in the direction of this new polarizer, but it is reduced in intensity. And so that is telling us essentially that that this up and down polarization is composed of a little bit of this, a little bit less of this, a little bit less of this, a little bit less of this, nothing perpendicular, a little bit of that, a little bit more of that, a little bit more of that, a little bit more of that, and so on, sort of going all the way around. But when you are perpendicular to it, you will get zero intensity, and when you have some component of it going in the up-down direction, then you will get an amount of intensity that is based on that component, and we will get into the calculations for that here in a moment. But I just wanted to give a real quick introduction to, since I'm a chemist, I'm always interested in the chemistry of how this works. And so this is the way that polarizers that you would find in things like sunglasses would work. And essentially what they're doing is they have this polyvinyl alcohol, often called PVA, and they actually stretch it out. So this is showing a sheet of polyvinyl alcohol. This is a might be hard for you to read, but it says stretched sheet of polyvinyl alcohol, and that makes it so that all of the polymers that look like this are sort of oriented in the same direction. And then what they do is they actually dope it with iodine. So they have here potassium iodide. And then the iodine actually sits between these sort of parallel sheets of, or parallel polymers, I guess, of the PVA, because they have these hydroxyl groups here that can that can that can interact with the charged potassium and iodine. And then what that does is the doped iodine, so you can kind of see how that works here, where we have these iodines so if we have our two strands of the PVA, then they will sort of have the iodines kind of sitting in the middle there. This was obtained from crystal structures of it, so they can actually see where the iodines sort of sit in that structure. And then what that does is depending on which way these are oriented, so these can sort of pass electrons along each other, and so when light hits it, that will be polarized based on the way that these things are oriented. So if you stretch your PVA so that it's like this, then it will only let light that is polarized in sort of the left and right direction like this. And if you instead had it where you had your PVA like this with your iodines going down the middle, so that the electrons can sort of pass along this way in that chain, then it will only allow light that is polarized this way to move through. And that is how they actually polarize things like sunglasses, for instance. And so this is a very common type of polarizing material. Okay, so to understand the idea of light polarization, or at least when we are doing an experiment on light polarization, we first have to be introduced to the idea of the intensity of light. And I have the equation for that up here, where the intensity is equal to the number of photons multiplied by the frequency multiplied by Planck's constant divided by the incident area, which is sort of how much area you are hitting with your light. So if you are shining a light with a certain intensity and it's hitting that much area, it's going to look more intense than if you're hitting that area, because the photons have to spread out, and t is time. So you can imagine if you fire the same number of photons and everything at something that is this area, but you do it in 1 second, rather than hitting that same area, but you do it in 10 seconds, it's going to look brighter here. And so I have this, my excellently drawn light bulb here, and I show it sort of shining light, sort of going this way. And I have it hitting these little blocks here so that it's only allowing some of the light to get through. And so I think it doesn't take much time to imagine that the light that hits this surface right here is going to be dimmer than the light is right here, because fewer photons are going to get through. And so we can apply this same idea when we polarize light. So we have our light bulb here. It's shining light that's going through this polarizer so that it is now vertically polarized. And so I have this vertically polarized light moving through here. And then we want to test how much of the light comes through this polarizer here. So we have our light, it's vertically polarized. We want to see how much comes through here. And so what's going to happen is that you're going to get some light through, but it's going to have a lower intensity. And the reason for that is not all of the photons that are vertically polarized are going to get through. There is sort of a probability of the photon getting through, and that probability is calculated based on the angle that is between this polarization here and this polarization here. And so I made this little illustration down here. So if we imagine we have some vertically polarized light and it's going at some other polarizer. So I have up, you can see here the vertical I have as the longest, so we could say that that is 100% the length of this completely vertical one. Once you move over a little bit, then the length from here going down to here is a little bit less than 100%. Maybe we can say that that is 90%. And then we can keep going down, down, down until we get to exactly vertical, which is going to be 0%. And so you can imagine that there is that the light, when it's in this vertically polarized, when it's vertically polarized like this, is actually in kind of a superposition of all of these polarizations and everything in between, but I didn't draw everything in between. But you can imagine, I mean, I said this was 100%, and if you send this then through a polarizer that is perfectly vertical relative to this one, so they're the exact same, you will get 100% of it coming through. But you can imagine that there is sort of this superposition where it has all of this vertical component here, but it has a little bit less of this one. And as you keep going, as you keep moving down, you are getting less and less of that in your superposition. And so we can actually use the unit circle here to calculate how much less and less that would be. So this shows where the cosine is on the left here and the sine, so I'll put a little c here and a little s here. So that's just saying that when cosine is 0, that equals 1. When you have sine of 0, that equals 0. And then you can go up here, cosine of 90 is equal to 0, and sine of 90 is equal to 1 here, so cosine and sine. And so we can see here that the state vector that we are going to use, so maybe we'll call that the ket of theta, and we will say that that is cosine of theta sine of theta. So this is sort of our general state vector here. And so what you see with this is that if we have this as our general, then we can define something that is specifically pointing precisely to the right here. So we could even draw that as an arrow like that. That would be 1, 0, like this. And so then you can imagine too, if we then have one that's perfectly polarized upward, so we'll call that arrow like that, that is going to be 0, 1. And so these are sort of the orthonormal, well, these are orthogonal, and they're normal because they have a length of 1. But these are sort of the orthogonal or perpendicular states that you can have. And then you can imagine that there are multiple states that you could have in between. And so if we use 45 degrees, then that would be cosine of 45 degrees, sine of 45 degrees. So that is our ket vector. That is our vector there. So we are calling this 45 degrees. And if we go to our unit circle, we see that that is this square root of 2 over 2, which so I'm going to use 1 over square root of 2, which is the same thing, because if you just multiply by square root of 2 over square root of 2, which is equal to 1, square root of 2 times square root of 2 is equal to 2, and square root of 2 times 1 is equal to the square root of 2. And so that is where that square root of 2 over 2 comes from. But I'm going to use this. This is the one that you will see most often in quantum mechanics. So I'm going to use that. And you see that that is this case for both cosine of 45 degrees and sine of 45 degrees. And so you will end up with a vector that looks like this. 1 over square root of 2 and 1 over square root of 2. And if you go in the opposite direction, if you have one that goes like this, then that will be 1 over square root of 2 and minus 1 over square root of 2. And you could calculate for any angle in between here using this general version of the cosine and the sine here. And so for this, we can now start calculating some expectation values. And so we can start, so let's say that let's say that if we have one state, so if, and we'll call this if prepared with that and measured with this, then what we will get, what we have is we will have our expectation value, which is up, inner product with up, and we can then input our vectors up here. So that will be 0, 1. So we know that the bra has to be a row vector, and then we multiply that by the ket vector, which is a column, and that will be 0 times 0, which is 0, and 1 times 1, which is actually, no, wait, that I'm mixing that up. It should be 0 times 0 plus 0 times 1, which is 0. Remember, this needs to be a scalar. And then 1 times 0 plus 1 times 1 equals 1. So that's 1, and then we square it to get our probability, which is just 1. And so we know that it's 100%. If you prepare it in up and put it through up, it's 100%. You have 100% each and every individual photon. So each photon, I think I put an A there, but it should be an O. Photon has 100% chance to go through. And so we know that if we go back to our intensity equation over here, if this n doesn't change, so if this stays the same, we know that everything else is staying the same, then the intensity is going to be the same. And so we have the exact same intensity. So you sort of prepare it in up, so you send it through something that you have your unpolarized light here. It goes, now it is polarized up, and then you send it and you try to measure it coming out the other end of another upwards polarizer. You will get 100% of your intensity. So now, so let's say that we prepare it in that direction and then try to measure it in up. So that's taking our non-polarized light, we send it through some polarizer that polarizes it to the right. We now have a right polarized light here, and we try to measure it going through a fully up polarized light. So then what we will have is now we take our vectors. So this is the same one we have over here because we're still measuring it up. So that's 0, 1, and we multiply that. So now we are using the other one because we are now perpendicular to this one. So that would be 1, 0. So that's 0 times 1 plus 1 times 0, which is equal to 0. You square that, it's still 0. And you know that you have 0 intensity coming through here. And so you may have, if you've ever maybe used like polarized sunglasses, and you try to look through another polarized sheet, that if you take that sheet and you sort of rotate it around, you'll notice that at a certain point you can see through it perfectly clear, but then once you get it so that it's been turned 90 degrees, that it now becomes opaque, and this is what you are experiencing there. And you'll also notice that going between them, that the light coming through dims as you turn it through those 90 degrees. And so that would be if you did something like, so let's say that we prepare it, let's say we prepare it as up, and we want to measure it at 45 degrees. So this is going to be the 1 over square root of 2, 1 over square root of 2 as our row vector here, as our bra. And then with the up here, that is the 0, 1. So we see that that is 1 over square root of 2 times 0 is 0. 1 over square root of 2 times 1 is 1 over square root of 2, which 0 plus that is just 1 over square root of 2. If we square that to get our probability, that is 1/2. And so each photon that comes at our diagonal polarizer here, so each vertically polarized photon coming at this has a 50-50 chance that it will get through. So it has a 50-50 chance that it'll just get blocked and nothing happens, or that it will be able to move through here. And that is because it contains components that look like this. And so if we say that maybe this one is 45 degrees, that is 50% the length of this perfectly vertical one here. And you can imagine that the same as this over here, where if this is blocking half of the photons from getting through, then the light getting to this is going to be half the brightness of the light when it's over here before hitting this filter here. And it's equivalent to this in that some of these photons are being blocked and some of them are not. And it would be 50%, or 1/2 of them are being blocked, 50% are not being blocked. And so we can then sort of generalize this. Maybe we say that that we are going to measure it at some uh, at some angle phi after we've prepared it at some angle theta. So then what we have is we have the cosine of phi and the sine of phi as the elements of our vector here. Then we have the cosine of theta and the sine of theta as the elements of our column vector here. And then what we get with this is, I'm not going to go through all the calculations, I'll just tell you that it will be cosine of phi times cosine of theta or plus rather sine of phi times sine of theta. And this using a trig identity, which you don't have to have those memorized, but you can look it up, that this is going to be equal to cosine of theta minus phi. And because we are getting probabilities, we'll take this and square it, which means we square that. And so we are preparing in the theta and measuring in the phi. And so you can imagine if theta is equal to phi, then we have cosine squared of 0, which is equal to 1. And that makes sense. If these are both the same, then they are both polarized in the same direction. And that's exactly what we would expect, is that it would be 1, which is 100% of the photons are getting through. And if we say that theta minus phi is equal to 90 degrees, well, then cosine squared of 90 degrees is equal to 0, so that is 0%. And that makes sense. If this is 90 degrees, we already said that if you prepare in up and measure in sideways like this, that it will be 0 degrees. 0% of the photons prepared as up will go through the sideways polarizer. And so that is just sort of a little sanity check here, that this this generalized version of it does in fact give us the results that we would expect. And I think sort of the take-home message for this is that if you have light polarized in some direction, then you will reduce intensity as you start measuring it at different angles away from how you prepared the light. And once you get to 90 degrees, then your intensity will be 0. So we can imagine that if we go from 0, so if we go greater than 0, we'll call it theta up to, or which is, I think yeah, I got that backwards, sorry. Should be greater than 0. And then this is less than 90 degrees. Then we will have our, we will be between 100% intensity. So our intensity will go from 100%, so we'll call intensity I, down to 0%. And we can maybe even put equals to on here, greater than or equal to, and then less than or equal to. So this relationship is sort of, I guess, the take-home message as far as the calculations go. Sort of the why that happens, as I said, is the strange quantum mechanical effect that the light polarized this way moves towards your the polarizer that you are measuring with, and we'll say that it is this way. And not until it actually hits this thing will it randomly decide, and we'll say that it's 50%. We'll say that this is 45 degrees. So we say that 50%. So there's no way to tell before this hits this whether this single photon will actually go through or not. Once it hits this, something happens. So you might call it the collapse of the wave function or something like that. And there is a 50% chance that it will go through. So 50% through and 50% blocked. And like I said, before it actually hits your polarizer here, there's no way to tell. There's nothing you can measure about this photon that will tell you that it's going to go through or not. You can only calculate it as a percentage, which is yeah, that's sort of the weird thing about quantum things, is that it is probabilistic. I mean, there are a lot of people who don't like that and have attempted to come up with other things. So they're often called hidden variables. And so they're the hidden variable. It's hidden in the sense that if you look at this one photon polarized this way, you can't see anything about it that would determine whether it goes through or not. But there's the detractors of this sort of Copenhagen interpretation that says that it's just a wave function collapse, say that there must be some other thing that we don't know about yet, that our theory doesn't contain, or that we have not yet measured or something. There's some hidden variable that's determining which ones go through and which ones do not. But you know, you can look into that. So definitely one thing to check out for things like spin and stuff like that is what's called Bell's inequality. And I will probably make a video about that in the future. But if you're interested, you can look into Bell's inequality and the experiments from this, which tends to support the idea that there are not hidden variables, that this is a completely probabilistic, completely random. Random I don't like because that seems like it's just sort of chaos. But there is a probabilistic is better because there is a number you can put to it, even if it's only a probability. But anyway, that you can go off into much deeper, even sort of philosophical conversations about that. But I'm not going to get into that here. I hope you found this video enlightening and useful, and I will see you in the next video.